Okay, so as promised, I was going to record three different videos for you, or a video of three different examples for you, of various applications of pressure and fluids and all that kind of good stuff. So let's just start with a general pressure question. Susie Cream Cheese is wearing tennis shoes with an effective surface area of 60 centimeters squared. While wearing these, she exerts a pressure of 89 kilopascals while supporting her weight on one foot. So she changes for a night out into stilettos with a surface area of only 10 centimeters squared. So how much pressure does this shoe exert when she's only supported by one heel? All right, well, let's take a little look at what we can do with that. We know that pressure is just force divided by area. And to begin the problem, we know the pressure that she's exerting on the ground, and we know the area, or we at least can find the area of those shoes. Right? Well, to begin, let's actually find what that area would be. It's 60 centimeters squared, and then it changes to 10 centimeters squared. But that's not helpful. I need it in terms of meters squared. So let's do a quick little unit conversion. Because the unit is squared, it's not going to be good enough to just do one conversion factor of centimeters to meters. With centimeters squared, I've got to do it twice over. So I've got two instances of centimeters in the bottom. It cancels with the two instances of centimeters at the top, the 60 centimeters squared. And I'm left with meters times meters. That's meters squared. That's exactly what I want, and that's beautiful. So this area converts down to 0.006 meters squared. And I'll do that again. That's my initial area. I'll do that again for my final area. In just kind of a similar vein, 10 centimeters squared turns into 0.001 meters squared. All right, cool. So again, I start with pressure equals force divided by area. I now know the pressure in pascals, that's 89,000. And I know the area of her shoe at first in terms of meters squared. It's 0.006 meters squared. So let's solve for the force that she's exerting on the ground. Well, that's just going to be pressure times area. And that'll turn into 89,000 pascals times 0.006 meters squared. That gets me a force of 534 newtons. Now, this is a downward force she's exerting on the ground because of gravity's pull on her. So that force is going to stay constant, no matter if she changes shoes or not. She doesn't change her weight by changing her shoes. If only the world were that simple. So I can plug it just back into the pressure equation, except this time I know the force, the 534 newtons, and I know the area is now 0.001 meters squared after she changes shoes. All right, sweet. So that gets me a pressure of 534,000 pascals, or 534 kilopascals. So just by changing shoes, she went from 89 kilopascals to 534 kilopascals. And that's why high heels often sink into the ground, or if you're not careful on tile, can even crack a tile floor. Well, that's a general pressure problem. Let's go look at something that involves Pascal's principle, a hydraulic lift. It uses two pistons, one's big and one is kind of small. And if you exert a force of 250 newtons on the small piston with a radius of 2 centimeters, what weight could be supported by the larger piston with a radius of 20 centimeters, or what weight could be lifted? Well, this one is pretty much just a cut and dry Pascal's principle deal, where the pressure throughout the fluid connecting the pistons is constant throughout, or the change in pressure at least. And since pressure is just force per unit area, then I'll set up F1 over A1 equals F2 over A2. Let's go ahead and say that the small piston is location 1, F1 and A1, and the big piston is 2, F2 and A2. Well, now I just need to plug in what I know. Now, pistons are cylinders, and when you push on a cylinder, you're really just pressing on that circle right on the top of it. And the area of a circle is pi r squared. So I've got 250 newtons for F1 divided by pi times 0.02 squared equals F2 divided by pi times 0.2 squared. And check this out. We've got a factor of pi in the denominator of both sides of this equation. So that'll cancel. Then all I got to do is solve for F2. Well, plugging in your various values, you come out with 25,000 newtons. So by simply changing the radii by a factor of 10, I can now increase the force output that I get by a factor of 100, which is why these sorts of devices are really, really useful. Well, that's Pascal's principle. Let's look at one more example, and it's going to use the continuity equation. So let's say a child grabs a water hose. It has a radius of 1 centimeter. He turns the water on, and it travels through the hose with a velocity of 3.4 meters per second. Then he covers the opening a little bit with his thumb, and it creates an effective radius for the water to travel through of just 0.5 centimeters. So he's covering half of it. And then he points it at his sister. So what is the speed of the water as it exits the hose past his thumb? Well, this is just looking at the continuity equation of flow. I know the speed of the water inside the main hose with a certain cross-sectional area. Again, for a hose that's kind of like a cylinder, it has a cross-sectional area of just a circle. So if I know the radius of the hose, then I can figure out the cross-sectional area of it. Again, the continuity equation is just A1V1 equals A2V2, where A is area and V is velocity. So now, I just got to plug in what I know. Again, since the cross-sectional of a cylinder is a circle, the area is pi r squared. Notice that I changed my radii to meters, away from centimeters. So it's pi times 0.01 squared times 3.4 meters per second will equal pi times 0.005 squared times V2. Now all I got to do is solve for V2. Actually, pi cancels again. Beautiful. Now all I got to do is solve for V2 algebraically. And it comes out to 13.6 meters per second. Nice. So simply by just covering up half of the hose, he's changed the velocity from only 3.4 meters per second to 13.6 meters per second. And that's how powerful the continuity equation can be. So hopefully these 3 examples were somewhat helpful in dealing with fluids and pressure and all that kind of good stuff. You got a WebAssign with some similar questions on it, so good luck.